Okay, so the last screencast we just ended talking about RER, or the respiratory exchange ratio. So I just want to finish up talking about looking at what that is on a graph sense. So like I said before, as exercise intensity increases, right, so our relative VO2 peak, which is our oxygen consumption, which we've talked about, as intensity increases, our RER tends to increase as well. So as exercise intensity increases, we are shifting from using a lot of fats in our substrate into using a mix, and then into our pure carbohydrates once we are in kind of a sprint at that point in time. Now we look at this graph over here. It just is a good depiction of fat and carbohydrate use. Again, so it's VCO2 over VO2. So we've got our metabolism here and our respiratory exchange ratio here. So when we're at 0.70, we can see we're pretty much almost using 100% fats is mainly what we're burning as our main substrate to generate ATP. And then when we look over here, and then as exercise intensity increases, and so forth, or as we get over here to the 1.0 with our respiratory exchange ratio, we will see it up over here. We will be mainly using carbohydrates. All right, so let's talk a little bit about carbon dioxide. We've talked about oxygen a lot, so now we're going to briefly switch over to talk about carbon dioxide. So carbon dioxide is a metabolic byproduct of cellular metabolism, right? So carbon dioxide also follows a pressure gradient, just like everything else does. So CO2 travels in the blood 3 different ways. 1, as a bicarbonate ion. It travels that way about 60 to 70% of the time. 2, dissolved within the plasma itself. Or 3, bound to a hemoglobin. So it's called a carbamino CO2 complex for the most part. Okay, so we talked about oxygen and how that is exchanged from the ambient air to the alveoli into our tissues all the way down to the muscle level. And then now we're going to briefly talk about carbon dioxide's pressure gradients. So the P(a) CO2 is about 40 millimeters of mercury. So the arterial partial pressure of carbon dioxide is about 40 millimeters of mercury. So that's on the arterial side of circulation. Now the partial pressure in the mixed venous blood, so going over to the other side of circulation, that's P(v) CO2, is about 47 millimeters of mercury. That gives us a 7 millimeters of mercury of a gradient for carbon dioxide to be exchanged from the arterial blood into the venous blood. Now the partial pressure in the alveoli, P(a) CO2, is 40 millimeters of mercury again, right? So we have the mixed venous blood going back up to the lungs, and that again gives us only, again, a 7 millimeter of mercury difference. So we got 7 here and then a 7 here, which is pretty small. Right, so this only gives us a 7 millimeter gradient to move carbon dioxide from the arterial blood to the mixed venous blood, and then again from the mixed venous blood to the alveoli. Why is that okay? Why is it a 7 millimeters of gradient okay compared to the oxygen, who had a much bigger gradient of 60 from the ambient air into the alveoli, and from another 60 from the alveoli into our blood, right, to give us our mixed arterial pressures, right? We have a small gradient here, but that's okay because carbon dioxide is 20 times more soluble in water and moves 47 times faster than oxygen. So that's why we need a nice wide gradient for oxygen to move from the air to the alveoli to the blood. Now with carbon dioxide, we can have a much more narrow gradient because it is 20 times more soluble in water and moves 47 times faster. So we're really not compromising efficiency whatsoever with regards to carbon dioxide. Okay, next we're going to talk about something that's called a carbonic acid buffer system. And this is the equation up here. We got hydrogen, we got a bicarbonate ion. This enzyme is carbonic anhydrase. And then we have carbonic acid right here, and then again carbonic anhydrase, carbon dioxide, and H2O. So I'm going to explain how this works from blood to expelling it through our breath, and then how it travels in the blood down here. Okay, so this is an example how we buffer hydrogen. So we know as exercise intensity increases, hydrogen ions increase, right? So that makes sense. Hydrogen ions increase in conjunction with lactate. So if we were to do a lactate threshold testing and I were to prick someone's finger as exercise intensity increases, we would see an increase in lactate. we would know that an increase in hydrogen ions were also occurring with that due to the anaerobic metabolism occurring. And that's what lowers our pH. And again, that's a threat to homeostasis, right? So how do we buffer some of this excess hydrogen in order for us to keep exercising? Or how do we just do it in general, right? So we have, like I said up here, we have our hydrogen or bicarbonate ion, and this is what we're going to do. So we're going to combine a hydrogen with a bicarbonate ion to form carbonic acid right here. So we take this hydrogen that's being produced during anaerobic metabolism, we're going to combine it with a bicarbonate ion using carbonic anhydrase as the enzyme to facilitate this reaction. We will now form carbonic acid, and it's going to travel in the blood that way. Okay? Right, so right here we have our hydrogen. We're going to combine it with this bicarb ion, and we're also going to form carbonic acid right here, also using carbonic anhydrase. It's going to travel in the blood as carbonic acid. That's how it likes to travel. And then once we get to the level of the lung, so is this going to travel as a carbonic acid in the bloodstream? Once that bloodstream it gets to the level of the lungs, we're going to use the same enzyme, but that is at the level of the lungs. So the same enzyme, there's also one in the lungs. We're going to use that and break it into water, so H2O, and carbon dioxide. That's what we exhale into the ambient air, right? So this is how we buffer hydrogen and how we actually get it out into the ambient air. So in order for us to not have our pH decrease too much, right? Because our system likes to maintain homeostasis, and pH is a big threat to homeostasis. So a way for us to get rid of some of this excess hydrogen ions is to buffer it with bicarb. We'll travel as carbonic acid, we get to the lungs, we then break it down into carbon dioxide and water, and we expel it, okay? That is evident. So if again I were to put someone on the treadmill and put the mask in, again, that's all going to be then related to RER and what we're using as a substrate, because the more carbon dioxide we're producing, the higher that respiratory exchange ratio. So ultimately, we're really trying to get rid of this excess hydrogen and carbon dioxide within our system, and by doing so, this is one of our systems we can buffer. So this is a nice buffer system for us, and we can tell as exercise intensity increases, we can tell by the production of carbon dioxide into the air if we expelled it, if we measured those gases, as well as if I were to prick someone's finger. That's the next way. We're going to talk about lactate threshold next. Is the increase in lactate also gives us an indication that they're going purely anaerobic metabolism. Okay, next we're going to talk about our ventilatory threshold. What that means is this is the point where ventilation increases disproportionately to increases in oxygen consumption, right? So down here we see an increase in ventilation proportionate to oxygen consumption at that point, but our ventilatory threshold is right here where our ventilation increases dramatically without a same increase relative in oxygen consumption. Okay, when this, or if this occurs, it usually coincides with the onset of blood lactate, which is called OBLA. So OBLA is onset of blood lactate. OBLA is the point at which lactate accumulation exceeds clearance. So I'll say that again. OBLA is the point where we are producing lactate faster than we are clearing it. So lactate production is exceeding clearance. This occurs at about 4 millimoles per liter. That's important. So OBLA usually occurs at 4 millimoles per liter. When lactate accumulates in the blood, it will dissociate into a lactic acid and a hydrogen ion. The increase in hydrogen ion concentration will be sensed by the peripheral chemoreceptors, which then send signals to our respiratory center to increase the rate and depth of respiration. Right? So for us to breathe heavier. So, right, we've got to increase our rate and depth of respiration. Because remember, drive to breathe eliminates CO2 and all this excess stuff, and to also intake oxygen. So when this occurs, there's going to be a break in linearity of ventilation and VO2. So we see proportionally increases in VO2 as well as our VE, which is our ventilation rate up on the y-axis there. And on the x-axis down here, we have our VO2 peak. Right, so oxygen consumption's over here. our ventilation rate is up here, right? So then right here, our ventilatory threshold is where now we are breathing very, very fast. This is our threshold, right? So it's increasing disproportionately to the increases in oxygen consumption. All right, so now we're going to talk about some things called lactate threshold. So our lactate threshold is the point during exercise in increasing intensity at which blood lactate begins to accumulate again above resting levels. So we are producing lactate much faster than we are clearing it. So we're no longer to clear it or buffer it properly. Our exercise intensity is too high. And that's right here at lactate threshold. Usually, OBLA at 4 millimoles per liter is the onset of black lead type. That's usually when we start to see it in the blood start to accumulate. But our threshold is where we no longer can keep up with clearing it, right? So we are doing a decent job here during exercise. So someone's running, at 4, 5, 8.5 kilometers per hour, 10 to 11. But as the speed, aka intensity, is increasing, then at this point in time, this individual, boom, we will see a dramatic increase in lactate right here. So blood lactate, and that's usually coincides close to, this one shows 2 millimoles, but usually right here we can see it with 4. That's our first indicator that we are usually producing more than we are clearing. So right here, this kind of indicates right here, once we get that measurement, once we get 4 millimoles, we usually see the right here, okay, yep, now we're going to be increasing. So their lactate threshold is actually right here. Right, so with training, when someone says lactate threshold training, we want to move that threshold to the right, right? So for example, we see before training, if we were to measure someone up on the treadmill and we're to prick them or or on a bike, whatever type of exercise intensity they were doing, let's say running here, their lactate threshold here before training was about, onset blood is at about 10 kilometers per hour. Now, as one trains, we want to move that over to the right because that means we can actually clear the lactate much more efficiently as much as we're producing it. So our threshold now is to the right. Now, at almost 12 kilometers per hour is when we see this trained individual's lactate threshold at this point, which is what we want because that means we are being more efficient with producing and clearing lactate. That means the exercise task can A, last longer, or B, can be more intense. So this is what you see with training. So with lactate threshold training, we want to move that threshold over to the right. Okay, so here we see it increase disproportionately, and then over here with lactate threshold, we don't see it till about 12 kilometers per hour over here. So that means that person is getting better at producing and clearing lactate, which then the exercise task can last longer or then become more intense. Okay, so for our last slide, we're going to talk about this diagram right here, comparing two athletes. So these two athletes have, let's just say, consider them having the same VO2 peaks, all right? So they have the same oxygen consumption. Let's see, up around here, it's around, let's just say about 60. Let's round that both these athletes have about a 60 per kg per mLs per minute VO2 max over here, right? So oxygen consumption. The individual with the highest lactate threshold will most likely exhibit the best endurance performance. So we see athlete 2 over here hits lactate threshold at about 60%, and then this individual hits at about 70%. The reason being, even though they have the same oxygen consumption, you will probably see better performance out of that athlete in some sort of event or running event or anything. That person would either win or get nudged out or so forth, is because the person with the higher lactate threshold can tolerate lactate and a buildup of hydrogen ions and all of that waste better than athlete number 1. So the person who can who can produce and clear lactate better than the other athlete tends to have the better performance. That person can also tolerate those metabolic wastes much better. So that's another adaptation with moving the lactate threshold over to the right. They can tolerate those metabolic wastes better, so therefore you will see enhanced performance. So doing lactate threshold testing in addition to VO2 testing is important with different types of varying athletes' performances. Okay, so that wraps up the end of this lecture as well.